Hey everybody, we're live! I mean, put your headphones on unless you just want to sit down here and drink coffee, which is fine also. Totally acceptable. This is a very, very nice place to rest and relax, although I think there's better things to look at than us, so probably want to hear us too. So time to put on the headphones. All right.
Everyone, that's Dan Galpin.
Hey everyone, this is Sean McQuillan, and we're going to be talking about performance in a Kotlin world.
So to get started, I want to talk about some performance, maybe best practices. So one thing we can do when we're trying to increase the performance of our applications is we can just apply random code and advice we got from the internet. I don't generally recommend
really prescriptive, I think, already.
Fair enough, fair enough. I don't really recommend this. It doesn't usually lead you to the most performant app. Another thing we might try to do if we're doing performance is apply this concept of big O complexity that you might have learned about in school if you got a computer science degree. And if we look at a normal Android application, this looks something like big O of application plus database plus network, and then we'll do a big O analysis, and we're going to put those letters together, and then we're going to write a really hard proof, and return that 3 into a 2. And this is not a particularly useful thing to do for an Android application. One of the reasons that this doesn't really work very well in Android applications is the size of the data set we work with is typically very small in Android. Right? We're typically dealing with 100 or 1,000 elements. And so if we look at big O, we can see that this 7 becomes 70,000 very, very quickly as we go up to an n-squared algorithm. But if we turn that into time, that's actually only 10 milliseconds for some sort of realistic operation, which is a totally reasonable amount of time for the user to wait.
I feel like we're trying to put the audience to sleep already.
Yes, I love giving lectures. So there are 2 main use cases for big O complexity in your adult life. One, getting a computer science degree, super valuable. You should totally do it there. And the other, when you apply for a job at Google, it's also very, very relevant. So these are the 2 times you really need to know this stuff. And the third thing you could try to do for improving the performance of your application is just sit down, think really, really hard. Just go, I kind of know how CPUs work, I know how memory works. I have some ideas because I read things on the internet about how programming languages work, and I'm just going to think about it, and I'm going to come up with the best performing way to write my application. And this usually doesn't work out. And this works out opposite the way that it hopes for me on a regular basis. I'll sit down and I'll be like, oh, here's an optimization I can do. I try it and it makes things slower. This is a regular thing that happens to me, so I don't recommend this as your entire performance algorithm. So how do you do performance? So before we get there, let's talk about why you do performance. There's basically 2 reasons.
It's fun.
It's fun. So the first reason is you're doing it for work, in which case we would call this performance engineering. And I want to put an emphasis on the engineering part of that. We can also do it for fun. And when we do it for fun, it's called performance golf, which is a really, really fun hobby. And if you're into that sort of thing, I highly recommend it. But either way, there's really one way to do performance.
Use BASIC.
Yeah. The most performant language. So what you need to do is you need to define some sort of performance goal. You have to have some objective in mind when you're doing performance. Then you need to apply a measurement. So you need to actually measure the performance of your application to find out what you need to do to meet that goal. Then, if you haven't met the goal, change something. You do some analysis, think about what you should change. And then if you've met the goal, great, you're done. Otherwise, go back and measure and make another change.
Otherwise, use gotos. That's
Goto. Exactly. Goto fixes your performance problems. That is the point of this slide. The real key here is if you're not measuring, you're probably not doing performance. So in this talk, we're going to talk about 2 different ways to do measurement in Android on Android apps. So I'm going to pass it over to Dan to talk about profiling.
All right, so first of all, show of hands, how many people have used the Android Studio profilers? Excellent. How many people feel like they're really good at them? All right, that's about where I am too. Now there are 4 profilers in Android Studio now. There's CPU, memory, network, and energy. And running a profiling session looks like this. We've got the profiler loaded, we hit run. Our application's gonna run. This is the IO-Sched app for those who played with it. And the first thing we see is this timeline view, and this includes events, basically things like touches and also things like transitions. And we can see a touch event is right there, and that happened because the button over there got clicked. Pretty cool. All right, we'll continue on. All right, now we've actually seen our first actual transition. So we've seen now we're in a new activity, and that has shown us some things that are happening. Specifically, our memory has gone up. We continue on with that. We got a few more touches going on there in our app, and we've actually seen a couple of changes happen. One is that we saw a fragment transaction happen there, which looks like that, and we also saw another fragment transaction which brought up the dialog. Note the dialog is gone because there's a little bit of a delay between what's going on here, and that has showed us some memory as well. When that dialog went away, we actually saw the memory go back down the way we'd expect it to. So far things are looking pretty good. The app is working the way we'd want it to. And you can see that all in this outer view. Now we've just done another transition, and what that has brought us to is a bunch of networking stuff has happened, which is cool because we can actually go in and take a look at that. We can see that our memory has gone up, we can see that CPU has happened, and that actually is how this all works together with the energy profiler. So now we basically, networking plus CPU equals energy on a very high level. Let's take a look at that networking section again and see what we can actually, dig in there, what actually happened. Well, we can see that we've actually gotten these nice 3 things, which actually correspond precisely to the 3 things that were loaded by Glide, which is pretty cool. And we can actually take a look at what those mean. So we can look deep inside of these and see these goofy pictures. And we can also look at some of the details behind them. What's going on.
You just wanted to show a picture of Chet, didn't you?
Yeah, well, pretty much. It was all about Chet in this particular set of slides. So that's kind of the high-level overview of what you get at the very, very outside. But probably the most useful of these 4 is the CPU profiler. So I want to dig deep a little bit. And not all of you will actually get a review like this for your app. But app launching is a really important thing. And so let's look at a potential bug that you might have. You want to speed up how fast your app is starting up. Your product manager comes to you and says, slow startup. And it seems slow some of the time, which is always kind of frustrating because it's always nicer when things are always happening, right? But let's take a look at how you might look at the profiler to actually help you out here. So first of all, we have to run the profiler in a different mode for startup. We're going to go edit configurations, and we're going to go to the profiling tab, and we're going to say start recording our CPU activity on startup. And we've got a couple of choices here. We can sample, we can use trace. I'm going to use trace because I want to make sure I don't miss out on any methods that are being called. But sampling is probably good enough for most of what you'd want to do here.
What's the difference between those? What's sampling versus tracing?
Tracing actually uses features that are built into Art that actually return every single call to the profiler, or we actually instrument the code depending on which version of Android you have. Well, the sampling profiler is literally that. On a regular basis, we're seeing what's running, and we're just reporting that. So tracing is a lot slower, a lot slower. Do not look at trace as what actual performance is, and because we're tracing, when I talk about performance here on these slides, you'll see that it's actually quite different. So we've launched the profiler now. We're recording. We stopped. I've actually sped up time here. It does take a little while to parse and do all of this, but now you can see we've got this section we can move around inside of the CPU graph, and we're seeing a bunch of things that we might expect here, which is pretty cool. Probably most importantly is the bottom here is the timings for every call. And on the side here, we actually see the ordered calls in an appropriate way. So we're looking at the startup of an app. We're seeing exactly what we would expect here. We have system calls, which are in orange, and app methods that are in green.
I would call that a tangerine, I think.
Yeah, I think it's tangerine. So class loading is happening first. That's what we'd expect. And class loading is slow. There's a lot of things you can actually do to make class loading faster, but most of them are things you don't want to optimize for. So let's assume we're not going to be able to touch that. We have Firebase initializing. One of the things you probably know is that content providers get initialized before everything else in your app runs. Because of some of the things Firebase is doing, it wants to initialize first, so it's happening there. And then we actually get our application startup. We're using this JSR 310 library to do time zones. That's taking a little bit of time. And then finally, we have some dependency injection. And this isn't really dependency injection. What we're seeing here are a bunch of singletons all getting created. So if you have expensive singletons and you're using dependency injection, that's going to happen really early. So I recommend being very careful about that. These are all things that might cause performance problems in your own app. Now we also have a flame chart, and the flame chart is cool because it actually is ordered now by how long things are taking. Because we're running on the main thread, you can see that the bottom there encompasses the entire thing, which is our message queue. And once again, we can see that things are a little different order. Class loading is still first. Now we're actually seeing JSR 310 is the next thing. Firebase is way out there at the end. And these things are clustered differently. And why is DI not ordered? That's because DI is also happening in the application on create. That's all. So we're seeing what we're really seeing is the application on create separated out. We also can look at this top-down view. And this is kind of cool because it gives us a bunch more data. It's also really cool if you're the kind of person who likes to look at spreadsheets rather than graphs. I know there are people out there like that. But it has additional information. You can actually see the amount of time that was actually spent in the individual function.
What does it mean to be spent in a function?
That's a very good question. So normally what we're looking at, when you're looking at like the flame graph, you're looking at the aggregate time that's spent in that function and all the other things that it calls. While actually what we're looking at here is the amount of time spent in that function itself rather than the things that it calls into. And this is somewhat interesting in top-down, which is really kind of a different view of the flame chart. But if you actually look at the bottom-up view, this is actually, I think, a really useful view. You're seeing all of the functions in your app, and they're all ordered by how long they took. And if you go to self here and click on that, you're actually going to see how long these are taking. Now, since we know that actually loading all of our classes took the longest, not surprisingly, OpenDex file native is taking longer than any other function that we see here. So we're seeing what we expect, but if you saw something else here that was interesting, this would be a really good place to say, oh wait, maybe there is some performance problem I should look at involving these things. What's interesting is you can also drill down. You can say, well, this function is taking a lot of time. Where was it called from? And you can look down at the call stack and say, oh, well, maybe I'm just calling that too much. So that's how you use the basic profiler to do things. But we did promise Kotlin.
We did promise Kotlin,
yeah. Right, yeah.
It was like the title of the talk or something.
Yeah, I think it was.
So let's go look for some Kotlin performance problems. Are
there Kotlin performance problems?
I don't know. We're going to find out. We have a profile. Right. We're going to take a look.
So, yes.
Product manager Dan.
Yeah. Schedule is slow. Sometimes. Oh no, it always is slow. It's always slow. It's always slow. All right, that's good. We like that.
So I'm super excited about this bug report. Always reproducible performance problems tend to be much easier to find than sometimes reproducible performance problems. So because I'm looking for Kotlin bugs and I read the internet, I have a couple things that I might be looking for in my application. And we're using all of these features. We're using tons and tons and tons of lambdas in the code that we're using here. So I might be worried about all these lambda allocations. I might be worried about the closures these are collecting. We're using map, filter, reduce. We're using all of these collections extension functions. I might be worried about the number of times I'm copying arrays. Maybe that's causing some of my performance problems. I'm using by lazy. I might be worried about that being something that's causing performance problems because I'm using by lazy and it's more expensive than the thing I would allocate. And if I'm an old school Java programming language or JPL developer,
you're the only person who thinks JPL means that.
I am the only person who says JPL. I might be worried about int ? Autoboxing. I might think that this might be a cause of my performance. So I'm going to check in on all of these things, right? This code path executes all of these things very heavily, and I'm going to see if I find any evidence that these are problematic. I'm also going to be using view models, live data, and data binding. This feature was built using all of the Jetpack utilities. So I'm going to be looking to see if maybe we use these libraries wrong, or if there's something like going on here that we don't understand about the performance of these libraries as we go through here. So we've done the first two steps here. We've defined a goal, and now we're going to go ahead and measure. So what I want to do is when I open the schedule, I'm going to collect a recording of that, and we're going to get that up in the profiler. We can see those clicks there, and that's going to help me pick the right region so I know which section is actually related to the schedule loading. Now, first I'm going to dive into what's going on with these Jetpack libraries, and that's going to happen over in this onCreate section. There's a couple other things at the very top level that I see when I first explore this chart right here. The rest of the time is spent inflating tags. Now, these tags are actually used for a filter view. They're not visible to the user when they first load the screen. So it's kind of interesting that I'm inflating them and spending all this time on them when I load the screen when I have not yet shown the user the data they want. After that, I'm then going to render the main list twice, apparently. which is actually, in apps I've worked on, not a super abnormal thing to have happen. Yeah, OK, I'm not too worried about that, except it's happening twice. And then if I look through the rest of the threads, I can piece together a story that a database query was started way back in the fragment on create, and it ran until the list was actually shown. So there's some things I want to focus on there, but we'll come back to that in a bit. Right now, let's zoom in on onCreate and find out what that view model is adding. So the view model is adding this little bar right here. So that's the entire overhead of instantiating my view model. So I can pretty much stop looking at that to see if that's my performance problem. Then after that, I actually inflate a view. And this uses data binding right here. But if I dig into the flame chart, I can see data binding is adding absolutely no overhead over regular view inflation. So I'm not too worried about that. After that, I'm inflating a menu, which also may not be more important than that main data. So I might be interested in figuring out if I can defer this later. And then I have layout and draw. And then followed by that, I do that tags thing. So there's kind of like two obvious performance things right here. And both of them are actually caused by my usage of live data. I'm displaying a menu, and I'm displaying tags before I'm showing the main data to the user. And what I might want to do here is defer those so that they happen after the main data displays, because the user doesn't need those when they first load the screen, and then reorder everything so that I end up with something like inflate, layout, recycler view. And if I do this, the user is going to get to the data much, much faster. So everything is pretty good. We found our usage of live data was kind of something we can maybe improve, but view model, data binding, and live data added no performance overhead. Now let's switch over to the Kotlin side and scroll through to the section where we're actually binding the recycler view. Here we're doing a lot of Kotlin stuff. So I'm going to select the region where we're doing that double recycler view bind, and I'm going to switch over to the flame chart. So this has ordered calls. These are basically stack traces. And then at the bottom, I have the sum of the time in the call. All right, so this is actually kind of interesting here, because now I can aggregate a whole bunch of different calls together, which when I'm looking at a recycler view is pretty much always what I want to do, because the cost of doing on-bind is probably negligible, but doing on-bind thousands of times might be something that's substantial. So I want to kind of aggregate that together and take a look at it. So reading a flame chart is kind of a specialized skill that is only relevant to software engineers, and you probably only have to do it when you're doing performance. So let's take a moment and take a look at a flame chart. Here I have a function main that calls calculate, that calls sum, and then add. It also calls sum itself. So there's a couple things to note here. The sum function right there is actually represented twice in this flame chart, both when it was called by calculate and when it was called by sum, because it has different stack traces. In addition, calculate kind of has this area here that doesn't have a hat. And that area is actually representative of the time that was spent in calculate itself, as opposed to one of the functions that it called. Right, so this is how you read a flame chart. So just as a high level, this is like a really useful skill when you're digging into these things. So let's take a look at this flame chart. And when we dive in, we're going to find out that almost all of the time is spent in this thing called update schedule UI, which is some function somewhere in my code base. And then the rest of the time is spent in layout and draw, which is not unexpected. That's a pretty substantial thing I'm drawing right there. So if I dive in, and I'll skip this part where I like poke through the code for 20 minutes, and we find the performance problem, it is in fact right here. What I'm doing is I'm taking the list of sessions, which is hundreds and hundreds and hundreds of things in a list, and I'm calling map indexed, I'm calling distinct by, I'm calling map, and I'm calling toMap. And if you have read the Internet Performance Advice on Kotlin, you'll know that each one of these is making a copy of that list. So that's probably fairly heavy. So let's dive in there and run it in a profiler. So the profiler says the most time in this call is spent in truncate to minutes. The rest of the time is spent in pre-allocating header strings. After that, converting timestamps into time zone timestamps. And then at the very, very, very end over here, I have all of the work that is caused by those copies. So everything around hash set add, array list add, iterators, and allocating the pairs. I'm actually allocating 2 sets of pairs as I go through this thing, is insubstantial compared to the rest of the time that I'm spending in this function. So we went down entirely the wrong path there, and we were focused on the wrong part of where this code was spending its time. The actual time is spent entirely in here, where I'm allocating the time, I'm truncating it, and I'm creating the header. So there's like, calling back to the beginning, there's 2 things here. Don't just look at code and think real hard, go get numbers, because the numbers probably won't be what you expect. And then really really don't apply random code you read about online, or I would amend that for in conference talks as well. So the next thing we need to do is change something. So I look at this and I have to make a plan. So I have like 3 expensive things and 1 not so expensive thing that maybe after I fix the expensive things will become expensive. So the first thing I look at is these 2, truncate to minutes and time zone, don't really need to be happening here. These are something I could shove way over out into my data layer, and I could cache these so that I don't have to recalculate them every time I display this list. So I'm going to do that, and that shaves off most of my time. And then this header pre-allocation right here is still pretty expensive. It's enough time that I'm still worried about it happening on the main thread. So I kind of have 2 options here. One option, I have a lot of allocations happening, so maybe I could go the route of trying to reduce the allocations. But just for fun and to point out that like reducing allocations isn't always the fix to your performance problems, I'm going to add 2 more allocations to fix this performance problem and make the header initialization be lazy, changing my timings to look like that. So how am I going to do that? I'm going to go in here. Sessions indexed by minutes is the pre-calculated cached value that I got from my data layer. And now I'm just going to, instead of calling create header, I'm going to use a thunk, which is my old friend from Scheme, which is basically just a really lightweight, lazy object. So all this is going to do is, if it's not initialized, it's going to call that lambda and get a new value out. And then it's going to return that as the result of the getter from then on out. So this is adding another allocation for this thunk object. It's adding another allocation for this lambda. And it's adding a lambda capture. And it fixed my performance problem. So at this point, maybe I'm done. Maybe I fixed my performance problem. I've met my defined goal. Maybe I'm not. If I look at the performance of the app, actually, I find that I still have more work to do on my layout passes as well as on my data layer. So I asked a bunch of Googlers like where they would go with optimizing this. And these are the 3 main categories of advice I got. 1, we should cache the data and all transformations. So this is something that's a really good idea. We're going to cache that in RAM so that the next time the user comes to this list, or preferably the first time the user comes to this list, all they're doing is reading variables out of RAM and displaying them in a recycler view. There's no database query, there's no transformations, there's no maps, there's no nothing. It's just variables list. Next, I'm going to try to pre-allocate the views. This one got really hairy, and it involved using async layout inflator and trying to pre-populate a recycler view pool, which is going to lead to a working solution, but it's also going to be kind of hairy code. And then the last thing to work on is optimizing the layout and draw passes. Both of those are fairly heavyweight, and both of those have a lot of opportunity for optimizations. So these are all great things to do that are definitely going to improve the performance of the screen, assuming I measure and find out that they actually do that. But they all have kind of drawbacks. My cached data and transformations typically are going to involve a bunch of bespoke, difficult code to write. It's going to add a lot of complexity to my application to write this layer. Pre-allocated views are likely to be incredibly fragile. I'm going to use an async inflation, and I'm trying to like make recycler view pool do something it's not designed to do. This is probably going to break every time I bump those libraries. So like this is something that is definitely fragile, and it's going to add a lot of maintenance cost to my application. And all of this layout and draw optimization, all of the examples were like use pre-calculated text. That one was pretty good. And then it got a little bit more complicated after that. This tends to lead to bespoke verbose code. And it's also, these performance optimizations are also very fragile. They're going to be dependent very heavily on the Android and library version you're using. And the performance optimizations may not have any applicable effect when you bump those versions of the library. So you're introducing more maintenance cost to your application, more code, things are more complex. So it's important to take a look at kind of optimizations like this holistically. Is this worth it for the business case or for the user flow that I'm working at? Or is this something that is just increasing the complexity of my application, and the user is literally not going to notice that I did all this work and made things more complicated? And this gets to the main point. Fully optimized code that is like at maximum performance, is often very bad code. It often has very tight coupling between things that are completely unrelated to each other. It often has lots and lots of verbosity doing all sorts of weird things. And it often ends up calling weird functions that you normally wouldn't call that no one knows the name of. So this is something that you should be aware of as you go down the path of optimizing. You want to make sure that you are focusing on solving your defined goals instead of just adding fully optimized code everywhere you can. So now I'm going to pass it over to Dan, who's going to talk a bit about benchmarking.
All right, so a show of hands, how many people actually saw the benchmarking talk from I/O? OK, so I wish I would have used more of those slides, but I'm not going to do that. Benchmarking is all about stable performance, and there's a lot of challenges with actually getting stable performance on Android for benchmarks. One is that you have to make sure things are warm. because Android is always trying to run in low power, and it takes a little while for it to kick up and run into higher power mode. You also need to make sure that it's not overheating. You need to make sure that you basically are recreating the same conditions every time. That's what the benchmark library actually does. And I put up this slide because I wanted, for two reasons. One is that this slide actually shows the difference between code that's running in debug and code that is not running in debug, and how that benchmarks out. And it turns out that it's completely random, depending on what you're doing. So another important thing we do in benchmarking is we actually want to run release code rather than debug code, because it gives us a much better idea of actually how much time is being spent. Another reason for this slide is because you can see a bunch of the things down here are things we actually use the benchmarking library at Google for. So we're always looking to see, for all of these things that are in all our libraries and in the framework, how long they're taking. And we're making sure that they're actually not going up over time. And what we do is we actually kind of have a chart that looks like this with all the benchmarks in it. Now, we don't just look at one benchmark and say, oh, if we fell by a certain percentage, and say, all right, well, that means that we're gone. With every single commit, we're actually running these benchmarks, and we're saying, all right, how close are we? And we can see over time that we might have actually had a performance improvement. In this particular case, our time is dropped, which is pretty cool. And we're just using real basic math in order to calculate this, okay? Or in this case, we actually had a performance regression. Or in this case, it's just all over the place, because probably the stuff that we're working with is dealing with a lot of I/O, or and we're not actually seeing consistent performance at all. And even with the benchmarking library, which tries really hard to see consistent performance, we can't solve all of these problems. So the point of all of this, if there is really a point, is that what we want to do is reduce our time. Now, unfortunately, these kind of graphs really don't look very exciting. People don't like graphs going down, because we actually like our graphs going up and to the right. So when you're actually showing this to your manager, look at it like this. There we are, and say that's a speed up, even though we know that's actually going in the wrong direction.
How do you calculate that speed up? How do you calculate the speed up? How do you make that graph?
How do you make that graph?
Yeah.
I don't know. Tell us how you make that graph, Sean. If you have a good answer for this one.
So anyway, you just pick a baseline, and then all you have to do is just write a regular percentage formula to figure out how much you went up or down.
Yeah, it's all about what are you using for your various axes to make it look as impressive as possible. Exactly. All right, but really that was enough tips on what to do for your product manager. Let's actually talk about what this looks like. So. I actually did do this for this application. I started off by using Android Studio. If you're using Android Studio 3.5, you actually have to add a little variable in order to enable this. But you can actually say new and module, and a benchmark module, and we're going to call this module benchmark, which is pretty cool. This is what it gives you, a little example benchmark. What I actually did, though, was benchmark the code that's inside of IOSKID that bootstraps the conference data. And this is something a lot of apps have. You want to bootstrap the application with some data that's sent into it, and there's not a really fast way to do that. So you probably have some code. In our case, we have code that actually reads JSON. And fortunately, we had already gone through the application, and we had built an instant app out of it. So we had modularized the app and we actually had written a test for this. All of these things made this really, really easy. As you can see, benchmarking is a test framework. So once again, you can see we have this benchmark rule measure repeated, and inside we're going to do that over many, many times. And that's the only way you can measure consistently on Android. So if you want to measure how something happens once, this is not the library to use. It's going to go and measure it a whole bunch of times to try to make sure it's getting as accurate of a representation of what's going on as possible. Now, I was curious of how many times this was running. I added this log message, but I was like, but I don't really want that log message to actually affect the benchmark. So I can actually hide this time by using run with timing disabled. It's one of the beautiful things about this being a very Kotlin-enabled library. And now all of a sudden I can get my really slow log messages, and these really do affect the performance quite a bit. And it's not actually going to affect the timing of my benchmarks. These are all the basic ways you use the benchmarking library. Now to run this, I run it like any other test. So I just say run. And just to prove to you this actually works, you'll see that the benchmarking library is actually going to put up an activity, and that's just to make sure, again, we're running in the best mode for performance. We're actually using sustained performance mode here, so you can tell we're running at a device that probably has Daydream on it. And you can see the test ran to completion, and we're measuring it at about 1/10 of a second. in nanoseconds. So this is something I probably don't want to have running on my main application thread, because it's a tenth of a second actually would cause a little bit of a burst in terms of some jank. But let's talk about the final thing here in this talk, which is to talk about systrace, and Sean's going to actually do a live demo here.
All right, live demo time. So we're going to talk about systrace. So systrace is the last profiler. We left it for last because it's quite different than the other CPU profilers. In fact, it does quite a bit more than CPU profiling. My phone forgot what my finger looks like. Just a second. There we go. All right.
It's the sweat. It's the sweat. That's what.
So what we want to profile here is...
I'll get out of your way. You can see.
All right.
There we go.
So let's take a look at this phone screen right here. I want to profile the swipe behavior of this main recycler view list. And I'm focused in on this because in the 2018 app, we had some jank in this recycler view scroll. We put a lot of work into the performance of this recycler view in 2019, and I want to check to make sure that that actually worked out. So I'm just swiping, and then it's just flinging, and the recycler view is doing that big animation for me. So there's a lot of stuff going on there. There's the recycler view animation itself. There's all these on binds. If I've misconfigured things, it's also inflating layouts while it's doing that fling. So let's find out what's going on in Android Studio. Did I lose? And I lost my live demo. All right, so we're going to take another recording.
He's doing it live.
We're doing it literally live here. So in order to do systrace in Android Studio, and I want to mention here, there's a standalone version of systrace that gives even more data than the one in Android Studio does. And it's probably
and it also
worth
can take much longer traces. So if you want to take long traces, definitely use the standalone version.
And I would definitely recommend that if you need more data than what systrace provides. So you just trace system calls, and an IDE error occurred. And live demo done. Okay, so we gave it a good go, and we can talk about systrace afterwards. The big thing that you're going to get out of systrace that's really, really key is it's going to show you what happened on the main thread, and it's going to show you which frames got skipped. That's a particularly helpful thing in something like this, where what I want to do is do that fling animation, and then look, it's literally going to highlight in red every single skip frame, and I can zoom in there, see what each thread was doing during that skip frame, and kind of like build a story about what my phone was actually doing that caused that frame to not land.
Now the tricky thing about systrace is that it doesn't actually show all of the methods that were called at any given time. So what you have to do if you're really going to use systrace well is you actually can go and write code and say, I want to create systrace sections throughout areas of my app that I've identified as having critical performance problems. So what I recommend doing is actually using these in tandem. You can actually use the profilers to kind of determine critical sections and then instrument those with the systrace calls. The other thing you can do is actually instrument NDK applications. So systrace is a great tool for game developers as they're trying to figure out why they might be dropping frames. You can actually use NDK calls to instrument sections in your native code, and then see those show up really nicely in systrace as well. And you'll see all the choreographer do frames as they show up, and you'll actually be able to see, okay, I'm missing my frame budget here, and hopefully with the instrumentation you've added, you're actually going to be able to see why you're missing your frame budget. But it's a little bit more involved than using these profilers, which are really nice, which work just beautifully with code that's written in the JPL.
A lot more involved.
Yeah,
it's a big, heavy UI. It takes an hour to figure out what everything is.
And the other thing that's cool about systrace is you can actually see how Android is scheduling all of your workloads. You can go to all the individual CPUs that are built into whatever device you have, and you can actually see the workload across all of them. That allows you to see stuff like, well, maybe look at this. This thread is blocked. That thread is probably I/O bound because it's blocking. There's nothing else happening. Clearly, I'm seeing some of that going on. So if you're actually running through a section, like especially during initialization, probably a lot of this code is actually I/O bound, and so you're going to get a lot more out of going and using a tool like systrace, where that's really obvious.
So in summary, if you need to know literally what every CPU on your phone was doing, systrace is your tool. If all you need to know is the method calls, use the other profilers. It's much easier, much quicker. So that's going to conclude our session for today. Remember, please measure your code in order to do performance. Thank you.
All right. Thank you.